Hello everyone, welcome to the channel. And last time we built a amplifier. This is the previous amplifier we built using this a power transistor D882 with the resistors, capacitor, header, LED 3mm in size, green, ceramic capacitor, also a header. This is our previous amplifier circuit, and we call this a transistor amplifier fixed bias circuit. So this amplifier is commonly used, mostly use this type of biasing, circuit biasing transistor. So the input supply here, voltage, is from the cell phone. That is the input signal. We're going to amplify the AC signal and then inputting that into the transistor and then outputting or output to the speaker. We have these arbitrary values of the collector resistor, 1 kilo ohms, and we computed the value of the base resistor using KVL. Computation here, and we also have this a layout for our header, the components, the speaker output header, and that's the previous circuit. Also we have here a power LED. So that's this is the previous amplifier. So let us see how this works. I'm using iPhone 4S for voltage input supply. We're going to amplify the signal from the cell phone. This. Hello everyone. We have a new circuit here. We're going to test our new amplifier using we're going to amplify the signal from the output jack of the cell phone, and we are also using this a speaker concert 4 to 8 ohms. This is a tweeter type 80 watts peak, made in China, sound of Denmark. So let us build the previous power on the circuit using
Transistor
our
D882 and
our diagram. Using our diagram, we're going to connect the circuit with our power supply 12 volts positive supply to our previous circuit, then connect the positive supply and then the negative supply of the 12 volts. Let us connect that. Then we have now the supply. You see the power LED on, and then we're going to connect the input. We're going to amplify the input, the signal from the cell phone. Okay, using headphone jack to the cell phone, and then the output is now going to connect to our amplifier using some alligator clips. The positive, then connect it to the header of the input header, and then connect the negative ground to the header. Let us see the negative of the cell phone jack. Again to the header of the input header. And then the output, speaker output to the negative. Negative should be in the negative. Negative of the header. The positive of the speaker to the header of the amplifier. Then we have this. Let us now test our previous amplifier using the cell phone.
Hello everyone, we have a new circuit here. We're going to test our new amplifier using Transistor D882. And this is a voltage divider bias configuration, common emitter. And we're trying to make the circuit. Also, we have this circuit.
As you have hear the sound, there's a little hissing sound or some sort of noise. Although this type of circuit is commonly used, a transistor fixed bias circuit. So I decided to build a new one, and that is the using a voltage divider bias configuration. This is now our new module, a voltage divider bias configuration. Unlike the previous one, that is a fixed bias configuration, this is a voltage divider bias configuration or circuit. We have a big capacitor here, also a power transistor D882, so a header, resistors, capacitor, header. This is an input-output header. This is power header. This is power LED. Some resistors, and this is now our new module, voltage divider bias configuration. So let us see the workings. Let us connect now using our circuit here. Let us connect now the power supply. Connect it. Also we have 12 volts power supply. Connect the 12 volts power supply to the input header or the power header, positive to the positive, and then the negative should be in the negative. Let us connect the negative to the negative. We have now power on LED. The circuit is on, and then we're going to connect the speaker. let us use another one, the same speaker, same as the previous one. This is also a concert, the same. Let's connect this is now our output. Since we don't have available, let us connect the positive to the positive of the output of the header, and then the negative to the negative of the header. Oh, let us use again the input from cell phone jack to test the circuit. Now we have this, a voltage divider bias configuration. Let us now use our cell phone to provide the voltage supply. Okay, and we're going to play the video.
Hello everyone. We have a new circuit here. We're going to test our new amplifier using Transistor D882. And this is a voltage divider bias configuration, common emitter. And we're trying to make the circuit. Also, we have this old circuit. And we can test now if it's working or not. What is the loudness of this amplifier? Is it audible or not? Okay. Let's do it. Bye bye.
As you've been hearing the sound, it seems that the sound is much clearer than the previous one. The voltage divider bias has a clear sound, although the volume is lesser than the fixed bias configuration. But the fixed bias configuration has a lot of noise and hissing sound and distortion. So, although this is the most popular method of biasing the transistor, it has a great or a bigger input impedance. So we can see the circuit diagram of the voltage divider bias. So this one is the voltage divider bias configuration. Unlike the previous one we only have this, a resistor connected to the voltage supply. Only one. Same voltage supply in, collector resistor 1 kilo ohms, a coupling capacitor 104 in the fixed bias, and 1 microfarad for the output speaker. But here in the voltage divider, we have here a power on LED with 600 ohms limiting resistor. Also we have 28 kilo ohms connected to the base with 5 kilo ohms, a voltage divider bias, and then 10 microfarad 16 volts coupling capacitor from the header up through the header with the use of cell phone, that is the one providing the voltage input, iPhone 4S. And then the speaker, we have 4 to 8 ohms concert, 80 watts. This is the input output header. Now the input is going to the base of the transistor, and also we have here collector resistor 1 kilo ohms, coupling capacitor for the 700 microfarad 25 volts for the speaker, which is connected to the speaker, the output, the input connected to the cell phone. We're amplifying the AC signal, and then with the use of voltage divider biasing for the transistor, and then the amplified signal is here. And this configuration, I think, has a good quality of sound, although the volume is lesser, but it has a good quality of sound. And then we have this supply power header connected to supply using 12 volt supply, and then we have this layout, Perfboard Layout, that is the actual Perfboard Layout. You see this I/O header, input output, voltage in goes to the different pins, voltage out, the speaker, cell phone, and then the power supply 12 volts power header. This is the Perfboard Layout. And this is the schematic diagram with actual input output power header. That is the connection of the output input. So we can first let us see the previous this is the previous circuit. This is the computation. We're going to compute for the values of RD, R1, R2, if you're interested in mathematics, RC, RE, and that is given 4700 microfarad 25 volts, C2 coupling capacitor to the speaker for AC signal, and then coupling capacitor 10 microfarad 16 volts, that is the working capacitor for this circuit diagram voltage divider biasing of the transistor. The commonly asked question is, how do we get the value of this RC, RE, R1, R2, RD, or the LED? We're going to compute that using a standard formula. So we have here our standard format for computing the value of RC, RE, R1, R2, because that is the commonly asked question. So let us now see. Since we have the VCC here of 12 volts, this is equation 1. I'm using this formula. 45% of the VCC should be the voltage drop across RC. That is my requirements. I picked this standard format. For BCE, I use 45% or 0.45 of the VCC supply. And for voltage at RE, 0.10 or 10% of the voltage supply. So using this equation 1, We're now going to compute for the value of voltage drop across RC. 0.45 times 12 volts, substitution, using equation 1, we get 5.4 volts. Voltage drop across RC. Now we can use now equation 2 for voltage across collector emitter. 0.45 times 12 volts BC, substitution, computation, 5.4 volts. This voltage drop across collector emitter is now our Q point, operating point of our transistor. That is the operating point. And now using equation 3.10 BCC, we get now substitution 1.2 volts. For impedance matching, that is the output impedance, should be equal to the collector resistor. And I'm using 1 kilo ohm output impedance, the output impedance I mean. For impedance matching, output impedance must be equal to the resistor collector. RC should be equal to RL, that is the resistance of the load. Whatever the resistance of the load should be equal to the collector resistor. So it means RC is equal to RL. Since I'm assuming that the load resistor or resistance is 1 kilo ohm, must be equal to the collector resistor. So RC is equal to the load resistor. This is arbitrary values. So we got 1 kilo ohms. Using Ohm's law, we now compute for the values of the current. Since we know now the 1 kilo ohms, the value of resistor at the collector. We now using Ohm's law, voltage is equal to IR. Computing for the current at RC, we get now transposition, substitution, we know the value of the two, and then the current now is 0.0054 ampere. That is now the operating point of the transistor, the IC, collector current, which is 0.0054 ampere. We know now the value of the collector current. So using current gain, HAP is equal to IC over IB, where IC is equal to IC RIC 0.4, and I'm using HFP of 160. That is the datasheet of the power transistor D882. Substitution, we get now the base current of 0.000338 ampere. And using again transistor formula, we now going to compute for the value of IE, the emitter current. Since we know the IC, the IB, now IE is IC plus IB. Substitution, since we know the values of IB, IC, we got IE 0.0054338 ampere. Also, we can use this formula since B is equal to HAP is equal to beta, or beta, same. IE is equal to IB times beta plus 1, also a formula used. So we get now this by substitution, we know IB and the beta 1, we got 0.005448. That is now the current that flows into the emitter, IE. Using Ohm's law, by substitution, we know the value of RE. Using the voltage current, we computed that. So we get now 220 ohms. RE, that is 220 ohms. So for the required current to flow at IR2, we need at least 10 times IB, 10 times the base current. The current that flows in IR2 or in the R2 should be 10 times IB. That is in the requirements for this configuration. So we have here required value for IR2 is equal to 10 times base current. You know the base current here, and now we know the current of R2 is 0.00038 ampere for voltage stability. Now we're going to compute for the voltage drop across R2. So we're going to use this formula KVL. Voltage drop across R2 is equal to voltage drop at RE plus voltage at the base emitter. Voltage drop here is equal to the voltage drop across the BE and the voltage drop across RE. That is KVL. Substitution, since I'm using 0.7 volts standard value for the transistor, I got voltage drop at R2 1.9 volts. Using Ohm's law, we got here, we know the value of the voltage and the current in IR2 and BR2. We got now the value of R2, 5,000 ohms. So that is the value of R2, 5K, 5 kilo ohms. For checking, let us see, using Ohm's law, IR2 is equal to voltage drop over R. We know the value 1.9 volts, 5,000 ohms. We got current of 0.0038 ampere, which is 10 times the base current. So the required current that flows and the resistor we need is 5 kilo ohms, 10 times the current that flows into the IB and to the base. So the current here is 0.0038 and the base current is times 10 of this base current. So that's why we get this. So we accomplish the requirements. We achieve 10 times IB, the IR2. And now we have now the values. 28 kilo ohms, 5 kilo ohms, 1 kilo ohms, 220 ohms. Also, we can compute for the power LED here using KVL. For power LED, BCC minus BRD minus BD, voltage drop across the diode is given and data sheet of the diode 2 volts. Substitution, we got 10 volts voltage drop across RD, that is power on LED. And using Ohm's law, since we know that the current rating of LED to turn on is 0.02 ampere, that is given data sheet. Substitution, we got now 600 ohms. So we got now 600 ohms value of the LED resistor. So in here, this is arbitrary chosen value for the capacitor. I'm using 10 microfarad 16 volts for the AC coupling, because during the DC signal analysis, this capacitor is open. Also, this capacitor, only the AC signal is going to pass to this capacitor and amplify into the transistor, and then we have amplify signal here, which is 180 degrees shift, phase shift, shifting 180 degrees out of phase, 180 degrees, almost half of the input signal. So we get now here. Also, we can use this. Now we can see what is the value of this 28 kilo ohm, since we don't know the value yet. So we can use KVL. Let's compute that using KVL. Voltage drop across R2 is equal to BCC minus BRB, which is 10.1 volts. That is the voltage drop across R1. So we get now using Kirchhoff's current law, the sum of all the current in the node should be equal to 0, leaving and entering. So this IR1 is equal to the sum entering the node is equal to the current leaving the node, which is IB plus IC, leaving current. According to Kirchhoff's, we know the value of IB and IR2, so we get that IR1 is 0.00363 ampere. Using Ohm's law for the substitution, we get 27,823.69 ohms. I'm using 28 kilo ohms available resistor. That is now the value of R1, 28 kilo ohms. So this is now the DC load line. We know that the voltage at the collector emitter, we computed that. So using this formula, remember, from the voltage supply, BC is 5.4 volts. So this one is around here, 5.4 volts. This is in the x-axis, 5.4. And our operating point for the current IC, we computed that using here, 0.0054 ampere. So we get now the operating point of the IC and the BCE, 5.4 volts, 0.0054 ampere. That is almost in the middle of the DC load line. So there's a swing of AC signal here. So for computing the IC set, of course BCE is cut off, which is equal to BCC, 12 volts. For the IC set, we're going to use this formula. IC set is equal to BCC over IC plus RE. And we know that all the values there. And then we get 0.009756 ampere. That is now the value of IC set. We know the collector voltage CE, cut off 12 volts, IC set 0.009736. I also have this table for computed and measured, but we're not going to use this almost just for that is now how to compute for the values of the resistor. And we get now this, we get the RD limiting resistor 600 ohms, 10 microfarad, 16 volts, 28 kilo ohms, 5 kilo ohms, 1 kilo ohms, 220, this is 220, 4700 microfarad, 25 volts, the header, the power supply, the cell phone, the output speaker connected to the header, and then PCB layout. And this is now our final product. Let us check again.
Hello everyone. We have a new circuit here. We're going to test our new amplifier using Transistor D882. And
There is no noise and distortion, at least. Unlike the previous one, let us check again.
they're trying to make
Let us put the output to the output of the transistor. Okay. Something wrong with the connection. The connection is not good. Hear that? Oh, wrong. This should be this one.
Hello everyone. We have a new circuit here.
Although we have allowed signal volume level, but
Transistor D882.
a little distortion and hiss.
This is a voltage divider bias configuration.
But still
Common emitter. And we're
has a
trying
greater volume level, but
the circuit. Also, we have this old circuit.
a little distortion.
And we can test now if it's working or not.
It's up to you if you're going to use voltage divider bias configuration or the fixed bias configuration amplifier. But I think the voltage divider bias is much better because it has a good quality sound. No distortion, no hissing sound. And thank you for watching the video. And stay tuned for more amplifier circuits, actual amplifier circuits. Different amplifier configuration circuits we're going to build in the future. Just stay tuned to our channel. Bye bye.